Hello, everyone. I'm going to give another short talk on engaging with R. In particular, we're going to look at correlation, testing to see if correlation is zero or non-zero, and linear regression, identifying a line of best fit, the slope of that line in particular, and then testing if that is zero or could be zero in the population, and calculating confidence intervals. So I'm going to open this script that's related to what I showed in class, but slightly different. It's going to open in our studio. The first thing I have to do, again, is set my working directory. So I'm going to identify, as we've done so many times before, where this file is, get the path name, and now add to my script this working directory. Great. So the first thing I'm going to do is I'm going to set that working directory. Perfect. The next thing I'm going to do is read in this arm span height data set again. This is a simple, goofy data set that I synthesized. I can then look at the head of this data set again just to see what's in it. And we see there are two columns. One is height, the other is arm span. And these are height and arm span measured on 20 individuals, or again, synthesized to be on 20 individuals, measured in centimeters. So the first thing I'm going to do is just look at this data. I'm going to use the plot command. Remember, this is a function. It has two required inputs. One is a vector of entries for the horizontal or x-axis. The other is a vector of entries for the vertical or y-axis. In addition, I can add optional inputs that, for example, change the title. This main input changes the title. Xlab changes the x-axis label. Ylab changes the y-axis label. So if I run this, I see that plot in the lower right. And again, this is a plot of height versus arm span. So each of these points corresponds to one of the 20 individuals or observations in my data set. Great. So the next thing I want to do is I want to look at the correlation between arm span and height in this data set. And so again, correlation expects as input two numeric vectors, one for the values of one variable and the other for the values of the other variable. And so again, I can run line 8 where I have that first vector $$ arm span for the first, this arm span column, and then $$ height for this height column. And when I run that, what I see is an estimated correlation of 0.95 approximately, right? Which again is saying in this data set, it looks like height and arm span are super highly correlated. One thing to note for both plot and for this core function, the first input and the second input have to be the same length. And in particular, the first entry of this first vector should correspond with the first entry of the second vector. The second entries should correspond, etc. You want to be careful to make sure that this is happening. Again, if R gives you some sort of an error message, it may be that you don't have the vectors you think you have, and in fact have vectors of different length, or this correspondence is messed up. Excellent. So correlation just spits out that one number. Sometimes I would like more information rather than that one sample correlation. I would like to learn about what I think the correlation in the population is based on the correlation from that sample. And there I can use this core.test function. And what does that do? It gives me, again, that best estimate of the correlation based on my sample, but also tells me about a confidence interval for that correlation in the population, right? In the sample, the correlation looked like it was about 0.95, but in the population, my 95% confidence interval tells me, it's quite reasonable that maybe the correlation is between 0.87 and 0.98, right? That all of those would be consistent with the data that I observed, again, with 95% confidence. It will also run a hypothesis test to test if the true correlation is equal to 0 or not. And it gives me this tiny p-value, 0.00001. I think I got the number of zeros right, or 2. Maybe I didn't get the number of zeros right. But again, this p-value is extremely small and indicates that it's very unlikely that the correlation in the population is actually 0. And remember, a 0 correlation, linear correlation, would indicate no linear association. Here we have this correlation that is really unlikely to be 0, So we can say these two variables are linearly associated and are dependent. Excellent. So that's engaging with correlation, in particular linear correlation. The next thing we can do is look at linear regression. So again, this is really related to linear correlation, though slightly different. And the LM command is a really important command in R. It fits a linear model. In particular, in this linear model, the first input tells us what our sort of outcome is, or what our maybe dependent variable is, and what our independent variable is, or sometimes this might be an exposure. And so here we might think about regressing arm span onto height. So you can think about this as building a linear model also maybe to predict arm span as a function of height. And just to note, here we use this optional input data to note that arm span and height are coming from the data set or data frame called dat. So we could equivalently have written in this line lm dat $arm span tilde dat $height, and we'll see these would give equivalent outputs. Let's run line 11 first and just see what we get. So we run line 11 and we see the first thing it tells us is just what we ran. Great. And then it tells us, it calls these coefficients. What it really means is this is our best estimate of our intercept for a line of best fit in our data, 4.429. And the slope here is 0.9842. And so again, this looks very similar to what we got in class, a little bit different. I think the data maybe changed a little bit, or I rounded poorly before. One thing to note is it doesn't call this slope, it calls this height, in particular because in the future you might learn about multiple linear regression, in which case there are multiple different slopes. And the LM function can also be used for multiple linear regression. So again, this doesn't tell us about uncertainty or confidence intervals or testing yet. All it does is report the slope and intercept for the line of best fit. And we see if we run line 12, we'll get something very similar. It's a little less pretty, where before we had height, now we have dat $height, but the outputs are identical, so you could go either way. Excellent. So now it turns out that LM actually gives us a lot more information than that, but that's the only information that it by default outputs to the screen. So what I'm going to do is something that may seem a little funny, but remember, everything in R that is output from a function is really an object that we can engage with. And again, different functions output different objects, but often it is useful, rather than just having that object output to the screen, to assign that object, create a new variable, and name that object. So here I'm going to take exactly what I had in line 11, only now I'm going to take the object and I'm going to assign it to a variable that I'm going to call fit. So I run this, and now we see there's a new variable called fit. And now we can do different things with fit. And one very common thing that is done with fit, this object is sort of a linear, sometimes called a linear model object here. It is the output of this linear regression. One thing we can do is run this summary function that takes in one input, and we've seen summary before. Summary is actually kind of a multi-purpose function, but it can take as input what we got from an LM function. So here I can run summary fit, and it gives me different descriptions of that linear regression object. So what does it tell me? So, it tells me what command I ran to fit that linear model. It tells me something about the residuals. We're not going to worry too much about that. It also tells me the same two coefficients that I saw before, where it calls them coefficients, the intercept and the slope corresponding to height. It gives me a couple of other values that we're not going to go into detail on, but are useful maybe for engaging with the t-test under the hood. And then this last column is a p-value for testing if the intercept or the slope are actually zero in the population. Recall, these two numbers are estimates based on our sample, but we want to relate this back to the population. And it says, actually, the intercept may be zero. Our p-value for testing if it is a null hypothesis that it's equal to zero, the p-value is 0.74, right? So that doesn't give us strong evidence that the intercept is not actually zero. However, the p-value for testing if the slope corresponding to height is equal to zero, this p-value is incredibly small, which gives us strong evidence that the slope for height in this model in the population is not truly equal to zero. So again, we see a value in our sample that is indicative that there is a true relationship in the population. And then we get a couple of other outputs that I'm not really going to worry about too much right now. Some people may have heard of R squared before. That's related to the predictive strength of our model, just like correlation was. But again, I'm not going to go into detail on that. We didn't get confidence intervals out of this, but the confidence intervals are actually sort of still stored in this fit object that we created. And the way we engage with them is we use this confint function. So this takes in this output of our linear regression model and will give us confidence intervals. So if we run line 17, what do we see? Oh, we see confidence intervals. So first we have a confidence interval for our intercept. Remember, our best guess is at the intercept based on our data was 4.4 roughly. But this is saying a 95% confidence interval for the intercept of the line of best fit in the population is roughly negative 24 to 32. So, again, this is also noting, not that we really care about this, but we don't have strong evidence, for example, that the intercept is non-zero. Now, really what we probably care about is this confidence interval for the slope, with respect to height in this model. And here we see this 95% confidence interval spans from 0.82 to 1.14 and 1.15, right? Which is, again, essentially what we had on those slides. And so again, this is very far from zero. This says, in this picture on the right, the line of best fit had a slope of what? 0.98, but we didn't have that many points on the right sampled from the population. And so in the population, we believe the slope could be as small as like 0.82 or as large as 1.15, again, with 95% confidence here. We can similarly rerun this confidence if we want with a higher level of confidence. So let's imagine rather than a 5% confidence interval, we wanted a 99% confidence interval. We would just run line 19, where we've now included the optional input level equals 0.99. Great, and what do we see? We see slightly wider confidence intervals for both the intercept and the slope corresponding to height. Again, this is probably the piece that we care about. Oops. And so again, we would report then this confidence interval of 0.76 to 1.21 if we wanted to report, say, a 99% confidence interval for that slope. So, there are many more things that one can do with linear regression. Linear regression is one of the most powerful tools in statistics. It's quite flexible. You can learn about interactions. You can adjust for confounding using linear regression. Here, we're just engaging with one small piece, but I think it is an important piece, and this may come in handy for things like the homework you're going to engage with. Excellent. Thank you, and have a nice Thanksgiving.